Bob Hariri, welcome to our leadership conversations here as part of our Library of the History of Human Imagination series. We talked to a variety of leaders across all of health and medicine, and it's a pleasure to have you with us here today. And it's a thrill to talk about some of the things that you and I were chatting about just before we got on camera. So let's just dive right in after I say welcome. Glad to have you here.
Jay, it's great to be here. Thanks so much for the invitation, and it's good to see you again.
Good to see you as well. So the TEDMed community is a multidisciplinary community. We're not cancer specialists, we're not cardiologists, we're not healthcare professionals, we're not hospital administrators, we're not policymakers, we're all of those people. And Celgene is famous for being a cancer company, a cancer pharmaceutical company. But I think the world is changing. There is no more cancer as a silo. Tell me about how that change is affecting somebody like you.
That's a very, very good way of looking at this evolution of this industry, because as we mentioned before and have discussed in our earlier chat, cancer is a wonderful model where if you apply the right tools, you can begin to understand some of the phenomenon, the signaling phenomenon that triggers aberrancy in a cell's behavior. Why does a cell go bad? Why does a cell decide that it's going to suddenly become invasive and highly proliferative? Why does a cell decide that it's going to traffic out of a specific discrete area and wind up in another tissue system? Well, a lot of what Celgene has learned in its first committed battle to control this horrible disease, multiple myeloma, hematologic malignancy, has now been translated into much of the research activities that are leading us to better treat autoimmune disease, better treat chronic inflammatory disease. And I think that Celgene is a wonderful example of how an appreciation of the value of medical innovation and a willingness to invest in that reaps tremendous rewards.
We're living in an age where we are finally beginning to peel back the underlying instruction sets of life, both at the cellular level, at the nuclear level, at the protein level, and at the surface of the cell level. We probably need a new model and how to talk about that, and you and I have been chatting about it. Could you give me one briefly that you think might be a way for people to think about cellular activity and dysfunction?
So, Jay, as a guy who spent the last 15 years focused every day on stem cells and cell biology, I've gained a new appreciation that my friends like Craig Venter, who talk about the cell being the receptacle or the repository of our software, our human biological software, and I completely. I embrace that today because
at first you thought, oh come on, that's silly. That's some computer scientist trying to pretend he knows a little bit about biology.
That's right. And then you see gene sequencers, a guy can sit at a console and basically synthesize an entire genome on their own.
What does he know about biology?
That's right. That's right. And as somebody who started out as an engineer, I actually say, whoa, I can actually get comfortable with this. Right. But I'm actually now getting very comfortable with the concept that if our software resides in our nucleus and the cytoplasm of the cell houses all of those processing elements, like what you see in a computer, and that once the software is read, it ultimately is put into use in that CPU, that processing unit. Then I see the surface of the cell more like the keyboard, where depending upon which protein sticking out of that cell membrane happen to get touched and pushed in, you're giving different instructions on how that software should be read.
Sort of frightening to think that a cell has the keyboard exposed and that anything walking by can tap on the keys and suddenly the cell has to deal with it.
You set that one up for me to hit it out of the park, Jay. So that's exactly what I think. I think that as a cell takes up residence on a template or a matrix, a structural set of proteins, if those proteins aren't set up the right way, if the sequence of interaction with the cell membrane is not consistent with normal biology, you might tell that cell to do something very different. You might signal that cell to proliferate. You might signal that cell to change its secretome, what proteins it's dumping out into the soup.
So let's embrace that just for a second. So at the core of the cell is the nucleus, and the nucleus has got our DNA, and that's the operating system, if you will, right? And the operating system then expresses and tells the cell in the cytoplasm, here's what kind of cell we are, here's our job, here's what we make, here's how we make it, here's what we do, and here's when we blow ourselves up when we don't do it right. All the things that we hope a healthy cell will do. And then on the surface of the cell is actually sort of backwards thinking, or maybe not, is this keyboard, which is exposed to the world. And generally, the things in the area type correctly on the keyboard. The cells around me, the proteins around me, they're typing friendly messages on my keyboard, just like I'm operating my own computer. Once in a while, something bad comes along and starts smacking on that keyboard in ways it's not supposed to, and the cell says, well, okay, if somebody's going to knock my keyboard around this way, I can run an evil program just as much as I can run a good one.
That's right. I mean, if a paracrine factor released from a cancer cell happens to come by and hit Control-Alt-Delete,
yeah.
You know, you may send that cell haywire, and that may lead to a transformational event. It might lead to the cell undergoing apoptosis. I mean, there's lots of things here which when I sit back and look at the behavior of our stem cells in the laboratory or in patients, I wonder, is this a good model to follow? And would it actually enable, empower our scientists to come up with different tools?
The whole idea of stem cells has been caught up in an extraordinary political debate because the source of stem cells were so highly politicized. And without getting into it, let's just talk about the fact that it appears that that age is nearing an end, where we're going to be able, through the efforts of you and others, to turn back cells to their original, if you will, neutral state. Is that near? I mean, I know we have induced pluripotent stem cells already, but how real before that becomes something that's ordinary?
So you know, right now we are on the threshold of understanding how you program a cell to behave with all of the attributes of a stem cell, meaning that it's got the ability to differentiate in a versatile way, that it can be self-renewing, and so on. But what's interesting is that stem cells, when they kind of hit the scene, and were thought of as the next great technology in medicine, the big debate was, you know, not only source, but you know, what does a cell have to do to have a meaningful effect in a disease? So for example, one of the behaviors that a lot of stem cells share is that they can impact the immune system of a recipient. You put a stem cell in, and it does something to the immune system to make the immune system function better.
The immune system is a whole body system, whereas a cell is an individual unit.
That's right. That's right. And the high degree of orchestration that the immune system has to have in order for you to, in parallel, prevent an infectious agent from ravaging your body, repair your cartilage that you damaged playing soccer, control the movement of chemicals in and out of your brain. All of those functions have to occur in a very orchestrated way. Now, one thing I can tell you is that for stem cells to become medicines, you have to think about them in a much broader way. Cell therapy means taking a biological activity, an attribute of a cell, and delivering it because for some reason it's either defective or absent in the recipient's body.
It isn't the cells that are doing the work per se, it's the cells that are delivering the new instruction set or delivering the stimulus to the immune system.
Exactly. So a lot of
they're not magic bullets, they're like magic code.
They're code. Mm-hmm. And here's another analogy. In a lot of ways, I think that every stem cell, regardless of its derivation, thinks it's in a fetus. And when you put that stem cell back into a new recipient, that cell has a natural tendency to try and drive the system to that sort of perfect state that exists at the instant of birth. And the instructions that reside in the nucleus of that stem cell allow it to produce all the proteins that are necessary to maintain that high quality biological activity.
We have this word immune system as if it were an organ in the body like the liver or the heart, right? So I've always wanted to ask, is the immune system, which isn't any organ, of course it's the whole of the chemistry of how you make yourself safe on a world filled with threats, would you guess the immune system is more complicated than the human brain or less complicated than the human brain?
So, it's a hard question to ask a guy who's spent a lot of time in neurosurgery.
That's why I'm asking you.
I've got to tell you, I think that it's actually far more complex. And it is the one system that clearly interacts with every other functional physiologic system of the body. It's a platform for communication. It's a platform for policing behavior. It is clearly a system that allows us to interact with our environment properly, and it's educable. Like the brain, the immune system throughout the course of life is highly receptive to information. Right. It's adapting, evolving, yeah. and it is changing not only the messages that it's distributing, but the manner in which those messages are distributed.
There's this pivot going on in the world of medical science, and the pivot is from this age of silo expert specialists who were incredibly good at what they did to the generalist, or at least the multidisciplinary or multi-thinking expert who is capable of taking concepts from adjacent and non-adjacent fields and saying, wait a second, that applies in my world. And now with technology allowing us to share so much more, so much faster, we don't have to wait for that publication to come out in print 8 months from now, right? We have so many different areas of science that move at a speed that is unprecedented. We can start to ladder up a self-organizing approach to multidisciplinary attacks on these giant problems.
That's one of the great gifts that's been given to the biomedical community by the information community. Mm-hmm. And you're right, it's astonishing. Literally within hours of a publication being released, it's already hit virtually every scientist and laboratory who's interested in that problem.
That used to take months.
Would take months, exactly.
Years.
Exactly.
Right.
So I think that the pace of innovation is clearly accelerating, but it's our responsibility to continue to create the incentives and to permit innovation to occur and to allow that story of innovation to attract and retain the investment so that this pace continues to accelerate. What I worry about, and what we worry about at Celgene is that unless there's an appreciation that the long-term benefits of medical innovation aren't just a new drug to treat the same disease the same way, but rather drugs that can, and other tools which can change the equation around the management of that disorder. And then when you change that equation, it not only means the lifespan's extended, but that you return that individual to society, mm-hmm. and they can now contribute to society in a meaningful way. That has a direct impact on GDP. It has every cancer patient we save, every life year we save, has a tangible net benefit to society that can be measured in dollars. Look at HIV. Look at the way innovation turned a uniformly fatal disorder into a chronically managed disease, much like some of the cancers we've been talking about. The actual societal value can be measured in trillions of dollars. So when we're in challenging economic times, when everyone's trying to say, well, you know what, we just have to cut, because we can't sustain this amount of spending, the one thing we have to be very cautious about is doing anything to limit spending in innovation which has a direct, tangible economic benefit to society, like biomedicine.
So Bob, I want to thank you for the conversation here today. It confirmed a lot of what I suspected, and now I know that the immune system really is more complicated. I knew it was. But I also want to appreciate, on the behalf of the TEDMed community, you spending time out of your busy calendar joining us today on these leadership conversations. It's a real pleasure to chat with you.
It's always a pleasure seeing you. Thanks so much for the invitation.